Okay. Okay, ready? Hello? Okay, please respond quickly, okay? So let's start. Um, what we are going to talk about is nucleophilic substitution reaction. Okay. Nucleophilic substitution reactions with respect to what class of molecule. So this I'm gonna write as NSR, NSRs, nucleophilic substitution reactions. Okay, with respect to which groups of compounds or which groups of organic molecules? This is with respect to haloalkanes or haloarenes. Okay, haloalkanes or haloarenes, meaning you can either have RX or ARX, that AR stands for any aromatic group. Benzene ring with halogen, there could be any other substituent on the ring itself. We good? We're clear? Hello? There's a lot of static. Okay. All okay? Okay. So what is a basic structure of nucleophilic substitution reaction if we are talking about alkyl halides? This is what I expect the reaction to look like. Your alkyl halide, which acts like substrate. The molecule which we are paying the most importance on, we are seeing bond breaking and new bond formation in a particular group of molecule. Those are called substrates, right? With this, if we add a new nucleophile, that nucleophile Nu minus could be any nucleophile. For example, it could be cyanide, it could be hydroxide, it could be any of nucleophiles, either with lone pair of electrons or with a negative charge. Essentially, our nucleophile should be electron rich or electron deficient. Electron rich. And what is the substitution that we see here? Now the nucleophile replaces halogen, takes its place, and this is the new product, new substitution product that we get, right? RNU and plus X minus. What is X minus called? This is a halide ion. If it's Cl minus, that's a chloride ion. If it's F minus, fluoride ion, and so on. These halide ions can also be called as leaving groups because they leave and create space for the nucleophile to take its place, right? This is the basic idea of a nucleophilic substitution reaction. If we were to write a particular example of a nucleophilic substitution reaction, let's say I start with ethyl chloride, ethyl chloride, CH3, CH2, Cl, right? Plus, if we have a nucleophile of any kind, whatever comes to mind. For example, cyanide. If we take Cn minus as our nucleophilic ion, what substitution would we observe as a result? CH3, CH2, and then instead of Cl, we get cyanide plus Cl minus is our leaving ion, right? Here, cyanide tends to come from, so if we are obtaining a product which is alkyl cyanide and not isocyanide, that means it's most likely coming from aqueous KCN, potassium cyanide. If we were to give AgCl, silver cyanide, what would we get as the product? Because cyanide ions can act like ambivalent nucleophiles, can either attach from carbon's end or from nitrogen's end. If you switch out the nucleophilic reagent from a KCN to a silver cyanide, what are we obtaining? CH3, CH2, and now this becomes NC and isocyanide. Alkyl isocyanides would be obtained as a result, plus Cl minus as usual. We're good on this? Okay, the purpose of today's thing is not about embedded nucleophiles or which nucleophiles would cause which new product. It's mostly based on what we're going to talk about is mostly about NSR reaction mechanism, nucleophilic substitution reactions and their mechanisms. Okay, what are mechanisms? Pathways in which these reactions can progress, right? Okay, tell me something, Gaurav. What are, I'll tell you this, there are two pathways which are most extensively studied in 12th grade. What are the two pathways that we talk about with relation to nucleophilic substitution reactions? We have, bingo, SN1, substitution nucleophilic unimolecular, and SN2, substitution nucleophilic bimolecular. This is the name of SN1 and SN2. They are abbreviated versions of whether the reaction is unimolecular, substitution nucleophilic unimolecular is 1, or whether the reaction is bimolecular for SN2. We good on that? Okay, starting with SN2, I like to start the topic with SN2 mechanism first, and then we will go to SN1. All right. Now, SN2 mechanisms, I'll show you an example of how an SN2 mechanism would work with the example of, let's say we have, all good? Can you see the screen and all? Okay, with an example of methyl chloride. So we have H, one more H here, and then, oh, what happened to that? Sorry. Mm, okay. A hydrogen here and chlorine here. All right. So is this methyl chloride, CH3Cl? This is CH3Cl, and this is our substrate because we are observing the nucleophilic substitution happening in this particular organic molecule, right? Here, this methyl chloride reacts with, let's say, our nucleophile for today is hydroxide ion OH minus. So how does this hydroxide ion react with our substrate molecule RCl or CH3Cl? There are two directions from which the hydroxide, okay, the substrate that we just drew out, CH3Cl, is this a planar molecule or is this non-planar? So is the carbon sp2 or sp3 hybridized? Right, this is sp3 hybridized. So this is not a planar structure, this is a tetrahedral structure, right? So the carbon is sp3 carbon. Now, what does that give us? How does that help us to understand things? This OH minus can attack from two directions. The side which is closer to the chloride ion that's already there in CH3Cl. Get the point? The side which is closer to the halide or halogen ion that's present in your organic molecule Rx, that side we're going to call the front side. The opposite side we're going to call the rear side. Now, which side attack is more likely? Can the OH minus approach from the side where chlorine is already present or from a side where chlorine is farther away? Yes, it would attack from the farther side. One beautiful point is steric hindrance. One more point is that since halogens are electronegative, they would have electron density more on them compared to the carbon. So there would be electronic repulsions from the negative charge on the nucleophile as well as the extended electron density on the halogen atom. Get the point? So front side attack is, we call it front side attack is prohibited. Only rear attack is permissible. So as a result, what do we see here? We see here that there's the formation of pentavalent carbon. I think you remember this. Do you remember pentavalent carbon? What exactly is pentavalent carbon? So one second. What? Okay. So what is pentavalent carbon is that the bond is no, not positively charged. Positively charged is a carbocation. Okay. So what is going on here is that the new bond with carbon and OH, the new nucleophile, is taking place as this in the same time as the carbon chlorine bond is getting broken, right? This is called a pentavalent. The carbon is pentavalent because it has five things attached to it right now, although not with proper strong bonds, but still five entities close to it, right? So this is called a pentavalent transition state. And transition states are not equal as intermediates. Transition states are super unstable, very short-lived. All good so far? So what happens as a result of this transition state and the addition of the new nucleophile OH is that we obtain a new product where the alignment that you would see the stereochemical configuration would that be of an inverted molecule. So one second. Yeah. So the OH would go over here and we would have what? The Cl gets taken out. Okay. So one second. Mm, Why is it not drawing up properly? Okay, so we see something like this where initially the position where the chlorine was gets swapped out and OH takes the opposite position to that. And this configuration that we obtain as a result is called inverted configuration, okay, or inverted product, right? Any problem? No, do you have any doubts or something? All good? Okay, now we have a molecule with inverted configuration, inverted product. This product is our SN2 substituted product, right? Okay, so what was the point of SN2? Plus, there would be a release of chloride minus Cl minus ion. Now, what was the whole point of SN2, calling it bimolecular, is that it takes place in one step? Yes, this takes place in a single step, Gaurav. Okay, and what more is important here? The rate of the reaction depends on two things. What two things? Substrate's concentration, how much concentration you have of the starting alkyl halide, along with the nucleophile's concentration. That would also matter here because this is just happening in a single step. It's not a addition of two smaller steps. Get the point? Now, tell me something, what do you think would have the fastest reactivity? And by fastest reactivity, I mean comparing all alkyl halides between CH3X methyl halide and then 1 degree Rx primary alkyl halide, 2 degree Rx secondary alkyl halide, and 3 degree Rx tertiary alkyl halide, which would have the maximum tendency to move through SN2 mechanism. That means a single step attack and formation of product. Which would be more likely? Primary, or even more than primary, there would be the reactivity of methyl halides, but some books consider methyl halides as primary itself, so you can alternatively use primary or methyl. Now, primary would be even more prone towards SN2 compared to secondary, and then secondary would be more prone than tertiary. So by that logic, we can say primary reacts the fastest for SN2 and tertiary react the slowest for SN2, right? Any problem here? Now, give me the reason why you said primary would react the fastest and tertiary would react the slowest, given that this is our mechanism. Hmm. Yes. So, yep, exactly. So if we have big alkyl groups, let's say methyl groups, three methyl groups attached to this carbon on which we have our halogen, right? Maybe a Br group, I don't know. So what happens here is, since these alkyl groups are very large compared to normal hydrogen, yes or no? They will reduce a lot of steric hindrance on the approach of the nucleophile for SN2. So smaller the alkyl group, faster is the SN2 mechanism. Is that clear? Why? The only reason, main reason behind it would be steric hindrance, right? Okay, now moving on to the second type of reactions. We have enough time on our hands, right? Uh, I think we have enough time. Okay, let's move to SN1. Hello, any problem? Okay, SN1 mechanism. What do you think happens in SN1 mechanism? In SN1, this is unimolecular. So the first point is unimolecular. That would mean the rate of reaction would depend only on one thing, and that depends only on the concentration of our substrate. All good. And SN1 is a two-step process or a two-step mechanism. Please remember. All right. So what are these two steps that are involved in it? Step one would be, can you tell me what is the step one in SN1 mechanism? Step one is formation of a carbocation, right? So what happens? How does a carbocation get formed? Let's say we have tert butyl halide or tert butyl chloride. This is tert butyl chloride. Do you agree? Okay. So what happens initially? What happens is that the CCl bond gets broken. Chlorine carries the electrons of the bond as Cl minus and leaves as chloride ion, leaving group. That leaves us where that makes us have what molecule then? This tert butyl group with a plus charge on the carbon. So a carbocation gets produced as a result, right? And this reaction, the first step is usually a slow step. And if you recall slow steps in chemical kinetics, slow steps are a rate determining steps. They would determine the rate of the entire reaction, right? So that's why, since we only have substrate in our rate determining step, only reactant is the substrate, the rate of the reaction would only depend on the concentration of the substrate. Got it? Okay. Now, once the carbocation is formed, things are looking really easy for us. Now the next step is nucleophilic attack. Okay, nucleophilic attack of what? Nucleophilic attack of the new nucleophile. Yes, on the carbocation, right? All good so far? Okay, so now what we have is our carbocation CH3, third butyl carbocation CH3, CH3 plus, and then the new nucleophile. Here, nucleophile could be hydroxide, and this step is usually a very fast step, happens very rapidly because of electrostatic attractions, obviously, between negative and positively charged ions, right? So this forms our new product. Was this clear completely? Any question on this? Nucleophiles do not have a preference for SN1 and SN2. The alkyl halide, however, has a preference for SN1 and SN2. So if we have a primary alkyl halide, it would want to go through SN2. Why I'm saying is in SN1, we have a carbocation getting produced, remember? So here there would be a very important factor, which is carbocation stability, because SN1 is through carbocation mechanism. Got it? So what is carbocation stability? Which carbocations are max stable? Tertiary carbocations are more stable, followed by secondary, and then primary are the least stable carbocations, right? So carbocations of this nature, where the carbon is attached to three other carbon atoms with the positive charge on that carbon, these carbocations are super stable. These are most stable. Get the point? And if you have a primary, once again, if you have a primary carbocation, these are least stable. And secondary carbocation would have mid intermediate stability. Why they are most stable? That question, good question. That's because of hyperconjugation effect. Okay. What is the hyperconjugation effect? The more, so let's consider this carbon that has the plus charge as the carbocationic carbon. All the alpha carbons that are attached to the carbocation carbon, right? The hydrogens that are attached to them can have hyperconjugating effects. I'll not get into the details of hyperconjugation effects, but just remember the more the degree of the carbocation, the more hyperconjugating structures will be there, and thus more it would be stable, right? Not necessarily charge distribution, it's necessarily electronic movements. What I mean by that is let's say one of the hydrogens, they get released as H plus. So I'll just show you very quickly the mechanism, what is going on behind it. So I have CH, and one more hydrogen here, which is attached to a C plus and then more CH3 groups, right? I just expanded one CH3 to show you how this entire reaction happens or hyperconjugating structures happen. All good? Okay. So what happens here is that any one of the hydrogen can give out its bond electrons to the carbocationic carbon. As a result, what hyperconjugating structures would you see? Carbon, which is double bonded to the previous carbon, and then it has two hydrogens attached to it, and it would have a CH3 and CH3 group. Now, this carbocation's plus charge is mitigated because the bond of hydrogen electrons was given to it, right? And it forms a double bond. Now, this H plus, which was left alone, will just stay close in the vicinity of this alkene, and so it can fall back again to structure one. So hyperconjugating structures can oscillate between these two varieties. We get the point? So more is the number of hydrogens. See, the more the methyl groups, the more the number of hydrogens. The more is the number of hydrogens, the more hyperconjugating structures there can be. For a tertiary carbocation, how many hyperconjugating structures are possible? Since there are nine alpha hydrogens, so nine hyperconjugating structures with each hydrogen is possible, which makes it super stable. Get the point? Yes, it's more like resonating structures. So more the number of hyperconjugating structures, more is the stability, more the number of resonating structures, more is the stability. Okay, so this is what, we get the point? All good so far? Okay, so this is what makes tertiary carbocations most stable. Now, I have seen thousands of people confused that if tertiary carbocations are most stable, then why are they reacting the fastest for SN1? Um, Point is, look at the step. Did you also have the same doubt, by the way? If it is most stable, it should be least reactive, right? So SN1s, we didn't discuss that point. SN1's reactivity order is what? Which molecules react fastest for SN1? Reactivity order of SN1, hello, is as follows. Tertiary alkyl halides fastest, then secondary alkyl halides, then primary alkyl halides, and the lowest would be methyl halides. Okay, CH3X. All good so far? So the question still lies, why tertiary alkyl halides are the fastest to SN1? Since tertiary alkyl halides, the carbocation, tertiary carbocation formed are most stable. Most stable should mean they are least reactive. Is that the question that pops in your head? Okay, so the thing is, in the first step, there is a formation of carbocation going on. Which carbocation would the molecule want to form? The one that's most stable or the one that's least stable? Energetically, which carbocation would the molecule have the tendency to form? The carbocations that are most stable, right? So tertiary carbocations. That's why if in the first step, a tertiary carbocation is formed super fast because energetically they want to form that carbocation. Because step one goes faster, see, step one is the rate determining step. If this step happens faster, the next would automatically happen faster. As a result, can we say tertiary alkyl halides have the fastest reactivity to SN1? Because the first step happens faster for tertiary. Because tertiary carbocations are most stable. The molecule wants to produce that carbocation and then the rest just picks up really quick. Do you get the point, what I'm saying? Still have a doubt in this? Okay, so let's recap really, really quick. SN2 reactivity order, primary, then secondary, then tertiary alkyl halide, right? For SN1, it is the opposite. For SN1, tertiary are most reactive, then secondary, then primary. We get the idea. Any question, any doubt remains here. Okay, SN2 takes place through pentavalent transition state. Remember that? Okay, SN1 takes place through carbocation mechanism. All good? Okay, now we will try to solve some questions. How much time was actually consumed? 1 second, I have to check on it. 22 minutes. Okay, I have 5 to 7 minutes. Let's do one question after another. So this is question one for you on the screen. This is for people who are struggling with figuring out which molecules would react to SN2 faster or SN1 faster. Look at the degree of carbocation. Is it a primary? Is it a secondary? Is it a tertiary? And then try to figure stuff out. So the question asks you which would react rapidly through SN2. What do you think? The first molecule that we have, let's break this down. The first molecule that we have and the second molecule that we have. The first molecule, hello? Is it secondary? So alpha carbon and two beta carbons. This is a 2-degree alkyl halide. What about the second one? This is tertiary. Alpha carbon, 3 beta carbons. Beta, beta, beta. That means this is a 3-degree alkyl halide. So which would be more prone to SN2? SN2's order is 1, then 2, then 3. So which one? The first one, because this is secondary. Secondary have more reactivity than tertiary for SN2, right? Okay. For the next one, let's do this. This is asking for SN1, which would react faster and why? Again, degree. So this is the functional group. If you recall, anything, any carbon attached to functional group, alpha carbon, and there's 1 beta. So this is primary alkyl halide. And for the next one, this is functional group, alpha carbon and 2 beta carbons, right? Beta. This is 2-degree alkyl halide, which would react faster. For SN1, reactivity order 3, 2, 1. So second one, we are sure on this? Okay. Okay, cool. Next, if we look at these two, these two have a little different trick going on. Maybe I'll just quickly do it. I don't know. I feel like it would stop rolling. 5 more minutes. Okay, let's do this one then. Hello. Hey, what happened? You have to reply faster. I don't have much time. Hello. All okay? Okay, for the next question, for the third question, this is asking which would react faster in respect to with respect to SN1 and the nucleophile is OH minus. How do we get to decide that? what is the first molecule's order? So this is chlorine is the functional group. This is alpha carbon. There's one beta carbon. So this is a primary alkyl halide. With this, the second one, can you identify the second one is a benzylic halide? What's a benzylic halide? So, functional group or halogen bonded to a sp3 hybridized carbon, which is bonded to a carbon of the benzene ring, so sp2. This is benzylic halide, right? And please remember, benzylic halides are super prone, so CH2Cl, these are super prone to SN1 mechanism. Okay, they only go through SN1, they won't want to go through SN2. Why? First point, SN2 steric hindrance, benzene ring, very big benzene ring, steric hindrance. That's simplest thing to remember. Okay. One more point is that recall carbocation mechanism is there in SN1. That means this benzylic halide would produce a benzylic carbocation CH2 with a plus charge once the chlorine leaves, right? This benzylic carbocation is extremely stabilized. So I'll write this point here, benzylic carbocation stabilized through resonance. Okay. How resonating structures? Benzene will donate its electron density to this carbon with the positive charge. So there are a lot of stabilized by resonance. There are a lot of resonating structures, 5 resonating structures for benzylic carbocation. Get the point? This is very stable owing to resonance. Now, if it's very stable, it's going to form very quickly. So this would go through SN1 fastest towards SN1. Okay. So in this question, what is the answer? Our benzylic halide would react faster to SN1 compared to SN2 or compared to the other molecule. Is it clear? Any problem here? Okay, a very similar concept. One second. A very similar concept. Can you see the screen? Okay, a very similar concept is applied also to allylic halides. Now, what are allylic halides? Allylic halides look something like this. Let's say we have CH2, double bond CH, single bond CH2, and then a chlorine. This is called an allylic halide. So what's the specialty here? You have your functional group, you have your alpha carbon, which is sp3, right? All single bonds, sp3. You have beta carbon, which is sp2 part of double bond. Okay, is this clear? These ones, allylic halides, are also super prone to SN1. That means a carbocation mechanism. All right. Why? Because the carbocation which would be formed from this molecule, what carbocation? Cl would go away as chloride ion. That leaves us with CH2 double bond CH, single bond CH2 with a plus charge on this carbon. Yes. Now, these carbocations can be stabilized through resonance. What do I mean by that? Electron from this double bond can shift to the adjacent conjugating position to create CH2, single bond CH, double bond CH2. Now, this carbon would lose its positive charge because it's got an electron density in the form of a double bond, right? Okay, one second. This is double bond. Now, what would happen to the positive charge then? The leftmost carbon has only 3 bonds. So the positive charge would transfer to the other carbon. As a result, what do we have? 2 resonating structure 1 and 2. Because of availability of resonating structures in allylic halides, they also are these carbocations, allylic. So these are called allylic carbocations. Are we good? Allylic carbocations are very stable. Not as stable as benzylic carbocation though, because benzylic carbocation would have 5 resonating structures. Here you would have just 2 resonating structures. So still quite stable compared to the normal aliphatic ones or the normal alkyl halides. Okay. So that also makes allylic halides super prone to SN1 mechanism where carbocation gets produced. All good? Okay, now we'll just do one more question if time permits. Now, what is the answer to this? This is asking for SN2, which would happen faster and why. Again, figure out degree of the alkyl halide. First one is functional group alpha and beta. Since one beta, this is primary. And second one is this is functional group alpha. And how many betas are there? Beta 1, beta 2, beta 3. 3 betas, this means this is tertiary alkyl halide. So which would react faster towards SN2? What do you think? Primary reacts faster towards SN2 because SN2's order is 1, then 2, then 3, right? So this is the molecule which reacts faster. All good? Okay, maybe one more question if time is there. One second. Yeah, we're almost at the ending. So I'll just close this session now.